Good afternoon, everyone. So my topic today is involving Elixir library for computer vision tasks. So this is the GitHub repo for the library. It's called Evision. So the agenda for today is I'll be talking some current status from last year, and then I'll mention the Kino widgets that I have developed in the last year for this Evision library, and then I'll briefly mention how do we process images using OpenCL and CUDA with this library, and then we'll go through a interesting example solving a Sudoku puzzle, and so that's basically what we have, what I have for today. So first thing is that last year I mentioned that I want to make this library much more easier to interact with numerical Elixir, and now we have this ability to do that. And so for almost all functions that would take an evasion.mat struct before, it can also accept a NX tensor now, and sometimes you have to do this conversion between a evasion.mat to NX tensor, and so we can do that via this actually 3 functions. So the first one is quite obviously we want to convert the mat struct to a tensor, and then we can specify which backend we might want to use. So by default, it will be the evasion backend, but you can also pass it to like NX battery backend or TorchX backend or any other backend that is available. And then we have this from NX that will convert a tensor to OpenCV mat object in the Leaf world. And well, there is one caveat, so you may wonder why we have this from X and from NX 2D, because there is something that well, maybe I love and hate at both times at the same time. That is backward compatibility. So in OpenCV source code, so for example, maybe we can see this example first. If we read an image to using evasion.im read, then we have this thing here. We have 3-channel and 2-dimension images here. And we don't really need to have this dimension here, because we, for general matrix, we can identify its type by the shape. However, in OpenCV source code, because it has a long history, and originally it was specifically designed for processing 2D images, so they have this thing here, and then if we convert a tensor directly to a evasion.mat struct, then we will end up with a 1-channel and 3-dimension object here. So that's not. So some OpenCV functions will specifically check the dimensions equals to 2. So that is why we have to do this thing here. So this is really, sometimes it could be annoying, but we have to deal with it. And now we have this all pre-compiled binaries for most mainstream platforms covering Linux and macOS and Windows. Also, we have support for CUDA, and we also have pre-compiled binaries for that. Meanwhile, I also have this Erlang support here, and so this code here shows you can read a frame from your camera or some video files, and then you can resize it to to the input shape of that neural network, and then you can set it for as the input to the neural network, and then run the forward action, and then you get all the results from the neural network. So that brings the neural network with Evision to the airline. So I want to briefly talk about some CUDA widgets that I have been working on in the last year. So first thing that, so right now I have this function that I want to manually register all the smarter cells because I need to figure out a way to make it more tidy and save some space. So right now, after we register all the smart cells, we have some like decision tree and some random forest, support vector machine, and training data. Also, we have a larger one that is OpenCV model zoom. So for the tree variable one, it's basically you need to specify your data and your labels, and then you choose your data type and label type, and then maybe you want to split the data set to some training set and some test data set. Then you can save that to a variable. Then you can use that variable to fit it into a decision tree, and then you have some parameters here. And you can just fill in the numbers here, and then you can basically if you hit run in the Livebook, then you have this decision tree available to you, and the same is. And the same goes for the random forest, but now you have more parameters you can play with, and now you can do other things to make it suitable for your data set. One more thing is that we also have this support vector machine in the CUDA widget. So you have like max steps and max categories and some mean sample count to set for your SVM machine, and then you can do that. But okay, so next thing is the model zoom. So we have this face detection, face recognition, image classification, image segmentation, text detection, and text recognition. Those numbers after those classes are how many neural networks we have in the model zoom. And I think we need to double that because we have the quantized version for that, which is basically using some integer 8 or for the 16-bit float, the quantized version. Also, we support, actually some models only support running on CPU, but some models, they support OpenCL and CUDA, so you can choose whichever is most suitable for your hardware, and you can allocate your hardware based on your needs. So for example, this face detection one, unit, this unit, we have this top K parameter which you can set. We want the top 5,000 faces detected from the neural network, and we have this non-maximum separation threshold. Also, we have this confidence threshold for the model, and then you can choose. So for this model, we only have OpenCV backend, but it supports CPU and OpenCV as the target, as the compute target. So you can do that. So for example, if I set this using OpenCL FP16, then I can upload an image using the CUDA widget, or you can open your camera and take a picture of yourself, and then you can run this model. It will give you those 5 key points of your face or someone's face. So this is also I want to make this really simple. And another advantage using CUDA widget is that you can also convert this UI here to some code, and you can copy paste that code to your library instead of stuck with some GUI here. And then I want to mention the process images with CPU, OpenCL, and CUDA. So, sorry, maybe. Yeah, okay. So the first thing here is that we have this CUDA support here, and we have some required environment variables. Okay. Yeah. Okay. So the first thing is that we need to set Evision enable contrib to true, and then the second thing is to set Evision enable CUDA to true, so that we can use those modules from the OpenCV contrib repo, because CUDA support is actually located in the OpenCV contrib repo, so we have to set both to true. Also, we have this optional parameter here. You can specify the CUDA version. Now we have CUDA 11.8, CUDA 11.4, and CUDA 11.1 supported in the pre-compiled binaries. But if you compile from source, then you don't have to. You don't need to set anything for this variable. For Windows users only, you need to set CUDA runtime there to the directory that you installed your CUDA runtime DLLs. And then also, for all the CUDA-related modules, they are under evision.CUDA. For example, the DFT, you can do some free transformations, and you have this convolution thing and the ORB algorithms available. And there are some other things you can find that in the online documentation. So how do we actually do the computation on GPU? The first thing we need to do is to upload the image from CPU to GPU. You can do that in 2 ways. You can either do that in one single run. You can read an image and then use that result to initialize this GPU math, or you can have an empty GPU math, and then maybe you need to generate your image somewhere else, and then you can do this called the CUDA.GPUMath.upload, and then you specify which math you want to upload to the GPU, and then this is how you transfer the image data from your CPU memory to GPU memory. And then we can use operations under evision.CUDA star, like split, and it will split the image to 3 channels, or if the image has 4 channels, then it will split it in a 4 element array. And then you can do some transpose and some other operations on GPU. And after those operations are done, then you can download the images from GPU to CPU, and then you can visualize or present the result to users. So now let's see an interesting example here. At least I hope it's interesting. So this is how do we solve a Sudoku puzzle with Evision. So the first thing, we need to get the input image, which you can either take a photo or upload an image. And so here I'm using this one as the example. And then we will do some pre-processing. Basically, we convert it to grayscale image, and then we apply some Gaussian blur to the image so that we can better extract those digits and reduce the noise when you take the image. So this is the intermediate result after we apply those pre-processing steps. And then we will do a adaptive threshold. Basically, this will apply some algorithms defined in OpenCV, and it will give you a binarized image, and then we can do this bitwise lot the reason why we need to do this bitwise lot is because the training set we will use later is the MNIST data set, and it is so the digits are in white color and the background are black. So we just need to do that step so that we can get this image here. And from here, maybe you can see what we going to do next. Well, first we need to find the puzzle after those pre-processing steps. To find the puzzle, we need to call Evision find contours. So, and we pass some threshold and some other parameters so that we find those contours that specified by those algorithms. And then we can sort by the area of those contours, because the assumption here is that for a Sudoku puzzle, if you upload this image here, then we assume that the puzzle is the largest contour in the image, or at least it should be in the first of few contours when we sort that. And then we need to actually find that contour and use some use another assumption, that is this puzzle should be a rectangular, which means we have 4 corners, top right, top left, and bottom left, bottom right. So that which is why this 4 here, and we have this number 2 because you have x, y coordinates. And then we can, if we find this contour that has this shape, then it means that we probably find the puzzle. And well, for this example, as you can see, we indeed find this puzzle, and it's in the green box. And then, well, this is only located in the puzzle. We need to extract all the digits in the puzzle, and also we want to know which cells are empty, so that we can later using some other algorithms to find the appropriate digits to fill that cell. So for this step, I will skip some code here and just get to the interesting bit. Basically, we need to find the perspective transform matrix, and then we need to wrap perspective so that we can get the front view, so that we can transform it from this puzzle, from this angle to a front view. And then, since we know that the Sudoku puzzle is 9 by 9, therefore we can make it a square, so that we can to make it our life easier to extract each cell in the puzzle. And before we extract each cell in the puzzle, we need to train and test the MNIST model. And this training code here is really the example code in the Exxon repo, so I'm not going to repeat that for use. But basically, after we train this model, we can see that we have some accuracy is 96%, and then we can write this code here. We call Exxon build to have this predict function, and then we can pass the input cell to the predict function along with the model state, which is the trained model with those parameters to the predict function. And of course, we need to resize those input cell to the size we need, which is 28 by 28, which is the same as the MNIST one. And then, so this one here, so this thing here, this 8 is what we extracted from the puzzle, and then we call this predict cell lambda function, and then we pass the predicate function here and model state and the current cell, and then we can have this predicted result. So once we have this result here, we can simply do that for each single cell in the puzzle, and for those empty cells, actually we need to detect the contours in that cell. If we do not have any contours, or the contours or the area of those contours is really small, then it means the cell is empty, which we need to fill in a value here, and then we can have this thing figured out for us. Well, some digits are not correct in this example because we are using minist, which is the handwriting digits for machine learning tasks. And here we really have this those typed the digital fronts for on the image. So sometimes the accuracy is not good enough to have, but we can write our own data set, and then we feed that data set into the Evision training code, and then you can get a proper data set and a proper neural network model for your inputs. And then you can, if you run this algorithm again, then you have much better accuracy. So here so actually I stopped here because I figured maybe solving this Sudoku puzzle is not quite really related to this Evision library, so I probably will leave that as some thing I need to do another day. And yeah, okay, so that's all I have for today. Thank you for your attention. I'm taking some questions if you have any.
Thank you very much, Coco.
Yeah.
Questions? Yes.
So my question is related to the Model Zoo. So are there any plans to create sample material, for example, an interactive playground for your Model Zoo? Or is the plan to simply use Livebook for everything? Thank you.
Yeah, so my plan is, so actually I have a plan that I want to create some kind of a playground, and where you can have some blocks, and then you can have this input on the left side, and then you have the output on the right hand side, and then in the block, maybe that block could be image read, and then it will followed by another one. Maybe you can do some other pre-processing, and then in the end you can connect the output from the master cell to the input cell of that neural network model, and then you can get the result in the last output. So that's my plan, but my CS and HTML skill is not that great, so I'm still not sure if I can do that. So that's still a plan for now. Yeah.
More questions? Follow-up?
So my second question would be, among all the planned features, planned enhancements, whatever, what would you think would be the area that would benefit the most from community contributions? This is my last question. Thank you.
Yeah. Okay. So for that one, yeah, I think maybe there are two group or people maybe. So one group will be interested in all the image processing functions, and the other group will be interested in those machine learning things, either traditional ones or with neural networks. So right now, my priority will be focused on neural networks, but I'm open to any feedback from the community. So if you have any ideas, you can submit an issue or go to the discussion panel on the GitHub repo. So I'm 100% open to hear your suggestions. Yeah.
Yeah, something to think about, like how to use the community
Yeah.
that is around. Thank you very much for your talk.
Thank you.